Hey everyone, and welcome to this video on the Bernoulli equation. Bernoulli's equation is one of the most important and fundamental equations in the study of fluids. But before we can jump into using the equation in a problem, it's important that we understand the theory behind where the equation comes from. We're going to break this up into 4 simple stages. Firstly, what is the principle Bernoulli's equation is based on? How is Bernoulli's equation derived? Using Bernoulli in a worked example. And finally, an experimental demonstration of Bernoulli. Now, if you're already comfortable with a certain part, by all means, jump ahead. The links are attached in the description. So with that being said, let's get started. The principle behind Bernoulli's equation. Bernoulli's equation is simply based on the principle of conservation of energy, which states that in a system, energy cannot be lost or disappear, but is instead converted from one state to another. But what do we mean by this? You're probably familiar with concepts such as kinetic energy and potential energy, and we can use these in a simple example to demonstrate what we mean by conservation of energy. Here we have a simple pendulum. A ball on the end of a cord swinging from side to side. As it does so, its proportion of potential and kinetic energy change, but the total energy in the system, which in this case is the ball, remains constant. So if we freeze the ball at the top of its arc, all of the energy in the system, which in this case is the ball, is potential, determined by the expression mgh. Now, as the mass and gravity aren't going to change, the real variable here is h. H is the ball's distance from the ground. Now, we know that this value of h will change as the ball goes along its arc. And if this value of h is changing, so too is the potential energy in the ball. We can see that the ball has the least potential energy when it is closest to the ground. However, due to the theory of conservation of energy, if at the ball's lowest point it has the least potential energy, this remaining energy must have gone somewhere. This remaining energy was actually converted into kinetic energy as the ball went through its arc and gained speed. So here we have a clear example of the principle of conservation of energy at work. Even as the distribution between kinetic and potential energy change, the total energy in the system is constant at all times. Now you may be wondering, how does this relate to Bernoulli? Bernoulli's equation is simply an expression of this conservation of energy. But as it applies to fluids, we have one big difference we need to explain first. So a good way of conceptually understanding the idea of energy itself is to think of it as the ability to do work. Now we can use that. Here we have a very simple experiment to demonstrate what are the different types of energy in a fluid. We have a toy car sitting next to a bottle of water. And what we've done is we've cut a hole in the bottle of water, and for the moment we've covered that hole with a piece of tape. So let's look at what happens when we remove the tape. As expected, a jet of water shoots out and moves the car. Therefore, if the car is being moved, work is being done. And if work is being done, there must be energy at the location of the hole. And this may seem obvious at first, but let's say we place our height reference line at the height of the hole. Therefore, our distance h from this line would be 0, and therefore we would have 0 potential energy. Also, we know that the fluid in the bottle is not moving, so its velocity is 0. This means we also have no kinetic energy. But if we have no potential energy and no kinetic energy, where did the energy come from to do the work required to move the car? This is because in fluids there are not 2, but 3 types of energy: potential, kinetic, and pressure energy. And this is what our Bernoulli equation is. It's simply an expression of the principle of conservation of energy for these three types of energy in fluids. Now we begin to understand what our equation is about. In the next video, we will look at how the equation itself is derived.